Humans need resources. To get them, we need machines to get the resources and the methods to get them where we need them. To do these things, we sometimes use tunnels. Tunnels used for transportation are important since when there's an impenetrable barrier, it'd be extremely expensive to go around. So we go through or under it. There are large mineral deposits underground that humans extract by digging large tunnels to access the ore. Then we take the raw ore and send it to a processing plant to be turned into usable material. Tunnel boring. TBNs, or tunnel boring machines, are machines that use extremely large cutting implements to cut through either dirt or stone. The type of TBM is extremely important since some types of TBMs can't handle certain types of stone or sediment. TBMs can be up to 17 meters in diameter. Open TBMs have no shields around the front. Their grippers push directly against the walls. They are mainly used in solid, stable rock. Worth TBMs, Worth is a manufacturer by the way, have to alternate between pushing and drilling. Other makers of TBMs can have them push and move at the same time. Single shield TBMs have a shield right behind the drill. Right after the shield, a permanent concrete lining is constructed. The drill then pushes off of the lining. They can't drill and build at the same time, so they have to alternate. Dual shield TBMs have two shields that can move telescopically. The back shield acts like a gripper, providing pressure for the drill to move forwards. In dual shield TBMs, the front shield still has the lining constructed behind it. The main advantage of dual TBMs is that they can line and mine at the same time. Pressure must be put on the front of the tunnel to mine in soft soil with more groundwater. These are some soft dirt drills. Earth Pressure Balance, or EPB TBMs, collect the mud from drilling and pump it to the tunnel face to provide pressure so the water doesn't flow in. Occasionally, the muck can have additives added to it to stabilize the soil more. Like single shields, they make a lining and then push off of it. Slurry shield TBMs use slurry made from bentonite clay to provide pressure. The slurry then mixes with the muck, making it useless. So the slurry-muck combo gets piped to the end of the tunnel to be filtered and sent back to be reused. Open-face, soft-ground TBMs work in soil with low water inflows. They work forwards, and then precast concrete or ductile iron gets laid behind it. Then a wedge is pushed in, like pushing the ring out to fit the tunnel. TBMs also have backup systems like control rooms, electrical systems, muck removal systems, ventilation systems, and more. TBMs have several pros and cons. They are automatic and also safe for the employees. They don't disturb the surface at all and can work in hard bedrock or soft water-bearing soil or anything in between. They are also fairly fast. They also have lowish running costs. Finally, they lay the tunnel walls as they go. Their cons are that they are a pain to transport, and if you set them up on the site, then it isn't any easier. If they hit an irregularity in the ground, they can cause effects like movement on the surface or a tunnel collapse. They are extremely pricey. A good rule of thumb is $1 million for each meter in diameter in capital. Of course, there are alternative methods to just TBMs. These can be more cost-effective or just plain safer in certain situations. Drilling and blasting. Drilling and blasting techniques are exactly what they seem like. They use pyrotechnics and geology to blow up the rock. It is the main alternative to TBMs for hard rock drilling before TBMs were invented. The process of drilling is as follows. 1. Plan explosive placement. 2. Drill holes for explosives. 3. Partially fill the holes with explosives. 4. Fill up the rest with stemming, which is inert material. 5. Blow it up. 6. Remove rubble. 7. Repeat until the drilling process is complete. The tunnels can be supported by a few methods, like using ribs, bolts of varying types, and shotcrete, which is just shot concrete. D&B's capital is fairly low, but has high running costs due to its amount of manual labor. This makes it good for shorter tunnels. It is slower than TBNs as well. It can also be specialized for different rock types, like TBNs. All in all, it is still used today as a viable method. Cut and cover methods are simple. They consist of digging a trench and putting a tunnel in, and then covering the tunnel back up. Shallow tunnels, like a subway station, are the main use of CNC. This method has cons due to high levels of surface disruption. Land tunnels are tunnels that are made by having the land around them raised. This is normally in cities where the bottom floor is a parking garage. They have a pro in which they integrate better with the surrounding area. There are many more techniques and as many different ways to use them, but I hope you like this rendition of a few. Now I will cover the types of transportation that goes through tunnels. Tunnels can have cars going through them. They also have trains or just pedestrians. They are invaluable for transportation. They are also useful for the shipping of goods. According to Geographic, the Channel Tunnel, which is a notable tunnel in Europe, has a value of 203 billion Canadian dollars per year in trade. The tunnel also has 21 million passengers throughout the year. That is the entire population of Ottawa going through the tunnel 21 times in a year. As you can see, tunnels are very valuable. Combined with the sheer amount of tunnels, 475 in Canada alone, they have staggering values. Mining. Mining can take many forms. In any form, the premise is the same. Retrieve mineral-bearing ores. After the ores are retrieved, they are sent off to the refinery. According to the Natural Resources page on the Canadian government's website, Canada's mining industry is the leading global producer of potash and is ranked among the top 5 producers of aluminum, cobalt, diamonds, fluorspar, gemstones, gold, indium, niobium, palladium, platinum, tellurium, titanium concentrate, and uranium. As you can see, mining makes nearly everything you can see. Since I am focusing on tunnels, I'll only briefly go over other types of mining. Surface mining is the process of mining out in the open. It is cheaper and faster for shallow minerals, but also more environmentally taxing due to the fact that toxic minerals can be stirred up. It also has some subtypes of strip mining, mountaintop removal, and open pit mining. Surface mining makes gold, silver, and copper, among other things. Placer mining is simply scooping up sediment from the bottom of rivers where valuable minerals are deposited. It has minimal effect on the topography of the region due to the deposits being small and accessible. In situ mining is injecting chemicals into an ore body, letting the minerals dissolve into the chemicals. The minerals are then separated and the mining is completed with minimal effect on the environment and topology. Underground mining is used when there is ore that is deep enough under the ground. The reason it is not mined with other methods is because even though underground mining has a higher cost per ton of material mined, it has less material that has to be mined to get there. It is also 5 to 50 times less productive than surface mining. There are also many different types of mining for different ore body geometries. One of the most key deciding factors is dip. The openings made while mining are called stopes. The process of making stopes is called stoping. Stoping has two phases, development and production. Development is preparing the ore blocks for stoping, and the production is where the stoping actually starts. Development is significantly more expensive than production, so companies try to minimize it. If you get too deep, the pressure skyrockets. Over 4 kilometers below the surface, the pressure can get so intense that rocks can explode. Underground mining can come with high capital costs, including transportation, ventilation, and power systems. Shafts are the vertical elements of mines. Drifts are the horizontal elements. Shafts carry all the important resources like power, hydraulics or pneumatics, and water. Drifts can have numerous specialized uses like haulage, ventilation, and exploration. Drifts can be drilled in numerous methods. Some examples of different drilling techniques for drifts include drill drumbows, percussive drilling machines, and blasting. Percussive drilling machines use a bit that they slam into the rock face, then rotate. Due to the high energy of the collisions, and the extreme speed at which they take place, which is over 50 hits a second, they effectively chip through stone. Blasting methods are essentially just drilling small holes, packing explosives, and detonating them. The explosives used to be dynamite, but now an ANFO mixture is used. ANFO stands for ammonium nitrate and fuel oil mixture. Explosives may be placed in blast holes in the form of sticks or cartridges wrapped in paper and plastic, or they may be blown or pumped in. They are composed of chemical ingredients that, when properly initiated, generate extremely high gas pressures. These in turn induce new fractures in the surrounding rock and encourage old fractures to grow. In the process, rock is broken and displaced. For many years, dynamite was the primary explosive used underground, but this has mainly been replaced by blasting agents based on ammonium nitrate, which is AN. Its chemical formula is NH4NO3, and fuel oil, which is its chemical formula CH2. Neither of these components is explosive by itself, but when mixed in the proper weight ratios of 94.5% AN and 5.5% FO, the reaction will make completely harmless byproducts of CO2, H2O, and N2, and the not-so-harmless products of heat. All of these are present in the atmosphere and are completely harmless. If you put in too much FO, then it will make toxic CO gases. If you put in too much AN, then there will be toxic NO2 gases. So it's extremely important to get the ratio just right. That's really hard, so there's ventilation to replace the air. The blasts need to be sequenced so the rubble falls into the right place. The blasting cats formerly used were set on a fuse, but now we are transitioning to electric timers. After the stone is broken up, there are numerous methods of transporting it out. One is using trucks. There are also autonomous LHD units that load and unload themselves. There are also machines that sweep the rubble onto conveyor belts from a feeder chute that is dug out prior to rock removal. Scaling is done with a specialized tool that looks kind of like a crowbar. It can also be used with a mechanized arm with a scaling claw or impact hammer. Scaling knocks down all the loose rocks that could fall down and injure someone. It is an important element of the mining process. The methods used for reinforcing the walls are similar to TBNs and tunneling. A metal net may also be used if the rock chunks are smaller. Ventilation is also crucial. It is useful for clearing out rock dust, clearing out gases of poorly mixed explosives, clearing out diesel fumes, and more. The air must be climate controlled as well. That means if the mine is deep, the air must be cooled, and if the external air is cold, then it must be heated. Atmospherics are one of the main energy costs of a mine. This is leading companies to seal off unused sections of the mine and switch to electric equipment rather than diesel. Lighting systems are implemented along important thoroughfares, like in front of the main shaft. The miners are also equipped with headlamps and batteries to light their way. Larger mines can also have heavy equipment with bright lights on them. Water control is crucial for most mines. They normally pump or let water drain into a central sump. From there, it's pumped up a shaft to the surface. Occasionally, if there's massive amounts of water, there will be an extra chamber dug out to handle large inflows. Deposits with low dip are fairly common. They are formed where ancient oceans, lakes, or swamps used to be. They can be slightly distorted over time, but overall they stay flat. The common methods used for these are room and pillar mining and longwall mining. Room and pillar mining is a method where numerous parallel drifts are dug into the ore body with smaller perpendicular drifts connecting them at set intervals. This leaves pillars behind. In some mines, when the end of the ore body is reached, the pillars get dug out and replaced with a more permanent support. Longwall mining is better for softer ores like trona, salt, potash, mineral-bearing shale, and coal. The ore blocks are cut out in rectangular shapes, ready to have a cutting machine go back and forth along the face of the longest wall of the rectangle. There's a canopy above the miner that moves along with it, letting the roof cave in behind it safely. There is an armored conveyor belt letting out the ore as well. Sometimes there are steeper deposits with a dip of 55 degrees or more caused by other factors. These ore deposits can have different methods for extraction involving gravity. Blast hole stoping is a method where there's an undercut dug below the ore body. Then raises are drilled up to an upper tunnel. The tunnels are then blasted wider, letting ore fall down to be collected. Shrinkage stoping is a method where a smaller tunnel is drilled through the ore body. The ceiling is then blasted away layer by layer. The ore collapses down, ready to be collected. This method requires high strength of the ore and walls. It also requires a steep incline. Cut and fill mining has two variants. Overhand cut and fill mining is a method similar to blast hole stoping, where the ore is blasted down in layers from the side of the ore body. There are also drilling machines drilling out the bottom of the ore body. After the bottom drillers are done, the place where they just dug is filled with waste from the processing facility on the surface. The mining machines then engage with the open face made by the blast hole stoping and repeat. There's also a less common version of cut and fill mining called cut and fill mining. Sublevel caving is a method where numerous drifts are dug across the ore body. Then, small blast holes are drilled at periodic intervals above these drifts. Explosives are set off and letting ore and rock collapse onto the drifts ready to remove. The ore is removed and the next drift's explosives are set off. This method dilutes the ore with a lot of other waste rock. Therefore, it is best to use it with easily separable ore types like magnetite. In our home country, one province stands out from the rest: Ontario. It has horrible regulations when it comes to mine tailings. There are over 400 mine tailing dams, all of which are poorly documented and poorly regulated. This lack of regulation has been here for 2 voting cycles under the Ford government. What is the problem, though? Mine tailings are stupidly toxic. They comprise of fine particles, crushed rocks, dugout soil, water, organic and inorganic metals or metalloids, heavy metals, and radionuclides, all of which are extremely toxic. These can kill birds that even land in it. If poorly regulated, they can collapse. In 2014, there was a Mount Poly tailing disaster in British Columbia that will need decades more to recover, and the 2019 collapse of a dam in Brazil that killed 270 people. These collapses serve as an antibiotic, cleansing the land that it touches. These dams, if unregulated, are ticking time bombs ready to sweep away all life in an area. It is crucial that we take action when we vote to prevent this, and it is crucial that we are aware.